Google's new quantum chip accomplished something that sounds almost impossible. It completed a calculation in under 5 minutes that would take the fastest classical supercomputers on Earth an estimated 10 septillion years to finish. That is not merely longer than the entirety of human history. It is vastly longer than the age of the universe itself, by such an unimaginable margin that the number almost ceases to feel meaningful. The chip is called Willow, and at first glance it appears to be simply another breakthrough in computing. Yet beneath the remarkable headline lies a much stranger question: where did all that computational power actually come from? Some physicists suggest that quantum computers may not perform calculations solely within our universe. Instead, they may process countless possibilities simultaneously in ways that classical computers fundamentally cannot. If that interpretation is even partially correct, then Willow may represent far more than a faster computer. It could become the first real technology to force us to consider whether parallel universes are not merely science fiction, but an essential part of how quantum computation works. Willow is a 105-qubit quantum processor, and that number is significant. Traditional computers operate using bits, zeros, and ones that function like tiny electrical switches turning on and off. Every image, message, calculation, website, and video on the internet is ultimately built from these simple binary decisions. Quantum computers, however, use qubits, which behave very differently. Rather than existing only as 0 or 1, qubits can exist in multiple states simultaneously through a phenomenon known as superposition. When qubits become entangled, they can collectively process an enormous number of possible states at the same time. This is why Willow's achievement feels almost unbelievable. Researchers tested it using a benchmark known as random circuit sampling, a task designed to determine whether a quantum computer can generate outputs from extraordinarily complex quantum systems. For a conventional supercomputer, the problem becomes almost unimaginably difficult. It is not difficult in the sense of a challenging exam. It is more like asking someone to count every grain of sand on every beach on Earth, and then continue repeating the entire process for longer than the universe has existed. Willow completed the task in less than 5 minutes. That extraordinary result is why many people describe Willow as marking a new milestone in quantum supremacy. Google previously made a similar claim in 2019 with its Sycamore quantum processor, but that announcement sparked considerable debate because researchers later demonstrated that improved classical algorithms could significantly narrow the apparent advantage. Willow, however, appears different. The performance gap is no longer merely large, it is astronomical. The comparison is so extreme that classical and quantum computers almost seem to be playing entirely different games. Yet the benchmark itself is not the deepest part of the story. The real mystery lies in what the benchmark might imply. If a relatively small quantum chip can explore a computational space so enormous that classical machines cannot realistically reach it, then an unavoidable question emerges. What exactly is a quantum computer doing when it performs a calculation? That question opens a door many people assumed belonged only to science fiction. Quantum mechanics has always challenged our intuition. A particle can exist in several possible states until it is measured. A quantum system can behave as though multiple outcomes exist simultaneously, yet when we observe it, only one result appears. For decades, physicists have debated what this actually means. One interpretation argues that these alternative outcomes are simply mathematical probabilities, useful tools for predicting observations rather than physically existing realities. Another interpretation, known as the many worlds interpretation, proposes something far more radical. According to this view, the alternative possibilities never dissipate. Instead, every quantum event causes reality to branch into multiple versions. In one branch, a particle moves left. In another, it moves right. In one universe, a coin lands heads. In another, it lands tails. Every possible outcome exists, but each continues independently in its own branch of reality. Now imagine applying that idea to a quantum computer. When Willow performs a calculation, it does not evaluate one possibility after another the way a classical computer does. Instead, it manipulates many possibilities simultaneously. Under the many worlds interpretation, those possibilities are not merely abstract mathematical descriptions, they correspond to real branches of reality. In that view, The computation itself may effectively be distributed across multiple branches, with quantum interference allowing those branches to combine in ways that ultimately produce the final answer observed in our own universe. At first, this sounds almost unbelievable. Yet serious physicists have defended this interpretation for decades. Willow's remarkable performance has simply made the question feel more immediate. If the machine solved in minutes what classical computers would require unimaginably long cosmic timescales to accomplish, perhaps the explanation is not merely that quantum computers are faster. Perhaps they are exploiting aspects of quantum mechanics that have no equivalent in classical computation. Imagine a problem so complex that one person could never solve it, not in a lifetime, nor in 1,000 lifetimes. Now imagine infinitely many versions of that same person, each working independently in separate rooms, each solving a tiny fragment of the puzzle. Somehow, only the useful pieces combine into a single solution that appears in your room. While imperfect, this analogy captures the intuition behind the many worlds view of quantum computation. Under this perspective, Willow is not opening portals between universes or allowing communication with alternate versions of Earth. Instead, it may be taking advantage of the mathematical structure described by quantum mechanics to solve problems that no single classical computer could efficiently handle. That is where the phrase parallel universes becomes more than a dramatic headline. It becomes part of an ongoing scientific discussion about how quantum theory should be interpreted.